sometimes. So this last one is in some sense a complication on what we've done previously, but I also want to use it as kind of a summary to give an idea of what the kind of key concepts are. Okay. So I'll talk about multinomials, but also give a bit of a summary of what we've sort of learned. Okay. So we know, so let's just kind of think about our dealer, all right, with his 5 cards. So we know if the dealer deals all 5 cards out. So specifically what I mean is the dealer's got ace, king, queen, 4, 2, and we've got a position ready for the dealer to put each of those 5 cards. Okay, so card 1, card 2, card 3, card 4 and card 5. Okay, so takes a card out, places it over here, takes a card out, places it over here. Okay, without replacement, takes a card out. Now there's only 3 cards left to choose from, puts it here. There's 2 cards left now, puts 1 card in here, and there's a remaining card that's left over. Okay, so it doesn't put any of the cards back in the deck, but just places them 1, 2, 3, 4, 5. Okay, the number of ways that this can happen is, well, in this case, 5 factorial. Okay, there are 5 things that can happen to the first card. Okay, but once that's set, there's only 4 things left that can go into the next card, and then 3, and then 2, and then 1. Okay. Okay, but when the dealer deals 3 cards instead of 5 cards, sort of what's happening? What changes? Okay, so when the dealer deals 3 cards, okay, so gets the deck of cards, puts card 1, then card 2, then card 3, and doesn't put it back in the deck. Okay, effectively what's happening is we don't really care, the dealer doesn't care, or we don't care what happens with the remaining 2 cards, if they've been dealt or not. Okay, we could sort of imagine the situation where all 5 cards were dealt out and we just ignored what happened to the remaining 2 cards at the end. Okay, so if we thought of it that way, the dealer would take his set, excuse me, apologies, okay, and then would deal out the 3 cards. Card 1, card 2, and card 3, okay, and then in his hand would have the 2 remaining cards that he hadn't dealt out. So he'd essentially put 1 card in here, 1 card into here, another card into here, and I suppose it was ace, king, queen. What he'd be left with is a 4 and a 2, and we wouldn't care whether it was 4 if he was to deal them all out, if it was 4 then 2, or if it was 2 then 4. Okay? So what that means is we essentially don't care about the order of what would have happened with the remaining 2 cards if they'd been dealt out. Okay, all that matters is the order of these 3. Okay. Okay. So in this case, the number of ways that you can, so when the dealer deals 3 cards, the number of ways that this can happen we know from our example where we did permutations, it's exactly P5 choose, so P53, okay, which was equal to 5 factorial divided by 2 factorial. Okay? So why is that? So essentially what's happened here is by removing the order for these 2 cards, we've effectively sort of divided by 2. Alright? So the outcome where we get a 4 and a 2 is the same to us as the outcome where we get a 2 to the 4, 2 and a 4. Okay? So there's half the number of things that we consider, so that's why we divide by this 2 factorial here. It's sort of because we don't care what's left in the dealer's hand. Okay, or the order of what's left in the dealer's hand. Okay? Then, when we deal or when we're dealt, when we are dealt 3 cards and the order doesn't matter, okay, so let's draw a picture of that. So now if the dealer has, I'll tell you what, I'll do it a little bit below. Okay, so we're in that case. Okay, so rather than this situation, okay, you can remember from our picture above that the dealer has ace, king, queen, 4 and 2. And what we get is we've got 3 slots in our hand that need filling. We don't really care what order they occur in. And then the dealer has 2 slots in his hand as well. Right? So we've gone from a situation where we had 3 cards where we sort of did matter what went individually into this slot to a case where we have 3 places but we don't care about the order of them anymore. And the same here. Okay? So the effect of that is, okay, so the number of ways of dealing cards now was as we gave in the combinations part, that 4th part. So 5 choose 3, okay, which was equal to 5 factorial divided by 3 factorial divided by 2 factorial. Okay, so notice, just to recap, when all the order mattered, we had 5 factorial. When we removed the order mattering from 2 of the elements, 2 of the items on this list, we divided by 2 factorial. Then, when we removed the order mattering from these 3 cards, we divided by 3 factorial from that previous term. 5 divided by 2 factorial, but another 3 cards we don't care about, we divided by 3 factorial. Okay? So rather than thinking of these things, permutations, combinations, and factorials as completely different things, what we're really doing is we're essentially taking something where the order matters and we get the total number of items, total number of ways of these things happening, in this case 5 factorial, and as we kind of knock out terms, these 2 don't matter anymore, so we divide by 2 factorial. The order of these don't matter anymore, so we divide by 3 factorial. Okay, so in some sense it's a method of essentially kind of knocking out terms, okay, when you don't care exactly if they're equal for each one, we just care about the set having all those elements in them. Okay, and so that's the way we kind of deal with the sort of overcounting that occurs when we sort of care about the order. Okay, so just to kind of show that point, I'll consider this kind of last multinomial example. Okay, so let's consider the following rule. I'm going to change the game a little bit as well. So you're going to play with a friend now. Okay, and you get 2 cards. Okay, and your friend gets 1 card. Okay, and the pair of you win, you, meaning you and your friend, win if you, meaning just you and your own, get an ace and a king in any order. So your hand contains an ace and a king, and your friend gets a queen. Okay, so the same as before. Okay, so let's just think about that case. So what's happening there? So we've got ace, king, queen, 4, 2, which is the original hand of the dealer. Okay, and this is going to change into the hand of us and the dealer. Okay, so your hand is going to consist of 2 cards. Then from that initial deck, your friend is going to have 1 card, and the dealer is going to be left with 2 cards. Okay? And so the number of ways of dealing out these cards, okay, well, you don't care if it's ace then king or king then ace, okay? So the number of hands, or number of ways of dealing here, was going to be 5 factorial for the total number of ways that I could deal out where the order didn't matter. Then, because it doesn't actually matter for the first 2 cards, the 2 cards I'm dealt, the order that they occur, I divide by 2 factorial, and then because my friend gets 1 card, we don't care about the order that they get that 1 card, divide by 1 factorial. Okay, and then finally, for these last 2 cards which are left with the dealer, which we don't care if they get a 2 and a 4 or a 4 and a 2, we once again divide by 2 factorial. Okay, so, and this is equal to, well, 5 factorial, which is 5 times 4 times 3 times 2 divided by 2 times 2, which is just going to knock out that 4. Okay, so here we can put like 5 times 3, 30, I think. Okay, so the probability that you win, you and your friend, I believe is going to be equal to 1 in 30. Okay, so in this case it has a name for it in its own right, though maybe it doesn't warrant that. Maybe we just understand that we're essentially we're thinking of how we're going to partition up this set. We're going to worry about which bits we care about the order occurring, which bits we don't care about the order occurring. But in any case, this sort of calculation is called a multinomial. Okay? The number of ways of dividing a set of size n, okay, into subsets of size k1, k2, up to say kr. Okay, so in this case it was 2, 1 and 2, such that the sum of these equals n, so we count all the elements, okay, is given by the multinomial n, which we write as n, k, and then we include each of the, in the list, each of these k's, and it's equal to n factorial divided by k1 factorial all the way up to kr factorial. Okay, so we multiply along the bottom each of these terms. Okay, so one way of thinking about that is that imagine we have a number of items like these ace, king, queen, 4, 2, and we're going to put, let's say we've got a bin. This is a red bin, an orange bin, or a green bin. We're asking what's the number of ways of putting the items into the different bins, so that there's 2 in this bin, 1 in this bin, and 2 in this bin. So that's another way of thinking about these kind of multinomial terms. So what I'm saying here is, just like we had the black dots and the white dots before, we could have we need 2 black dots on top of here, so 2 items need to be black. We say that 2 items here need to be white, okay, and then 1 item would be another colour. I could get another colour, let's get it, why not? And then 1 item red, okay. Okay, well, okay, so I hope that makes sense. Essentially, factorials count the number of ways we can reorder elements, and then we can divide by those factorials in order to cancel out the order within them. That's the main sort of takeaway message from this. I'll try to cover a number of more examples in another video so we get a bit more of an idea of how this plays out. But I think this sort of covers the main concepts, and you might want to go back to those concepts once you've tried a few examples as well. Okay, great, thanks.